Two important theories have been developed to explain the properties of acids, bases, and salts. These are the Arrhenius theory and the Bronsted-Lowry theory. Here we'll look at the Arrhenius theory. In 1887, a Swedish chemist, Svante August Arrhenius, proposed that an acid is any substance that releases hydrogen or H+ ions in water. An example is the gas hydrogen chloride, HCl. Looking at the Lewis structure of hydrogen chloride, we see that there is a covalent bond between the hydrogen and chlorine atoms. They are sharing a pair of electrons. However, the bond between hydrogen and chlorine is quite polar, and although it keeps the atoms together in the gas phase, when HCl is added to water, this bond is too weak to keep the H and the Cl together. When HCl is added to water, the molecule breaks up. The chlorine atom, being more electronegative than the hydrogen atom, takes both of the shared electrons with it. Because the hydrogen atom has lost its electron, it acquires a positive charge. And because the chlorine has gained one electron, it acquires a negative charge. It is now called the chloride ion, or Cl-. This whole process can be summarized by the equation HCl gas gives H plus aqueous plus Cl minus aqueous. Aqueous means that the ions are surrounded by water molecules. So Arrhenius pictured an aqueous solution of HCl as a collection of H plus and Cl minus ions floating around freely in the water. The water molecules are not shown here in order to keep the diagram simple. Water is given a blue color in this diagram. Because this is a water solution, the subscripts AQ for aqueous are used for the hydrogen and chloride ions in the equation. According to the Arrhenius theory, a base is any substance that releases hydroxide or OH- ions in water. An example is solid sodium hydroxide. Because NaOH is an ionic compound, solid NaOH is composed of a crystal lattice of sodium and hydroxide ions. Here we show a 2D representation of a few of these ions. When a piece of solid sodium hydroxide is placed in water, the polar water molecules attract the ions and pull them away from the crystal. This process is called dissociation. The dissociation of NaOH is shown by this equation. NaOH solid gives Na plus aqueous plus OH minus aqueous. So according to Arrhenius' theory, an aqueous solution of the base sodium hydroxide could be viewed as free and mobile Na plus and OH minus ions surrounded by water molecules.
Is a solution that has water present in it. Let's imagine dissolving a basic substance in water. According to Svante Arrhenius, when a base dissolves in an aqueous solution, it dissociates into ions and releases hydroxide ions. Here we see that a base, sodium hydroxide, is added to an aqueous solution. NaOH dissociates into sodium Na plus and hydroxide OH minus ions. Because the hydroxide ions are released in the aqueous solution, the hydroxide concentration increases. Therefore, NaOH is an Arrhenius base. Sodium hydroxide, when dissolved in an aqueous solution, releases hydroxide ions in the solution. Here we can see the chemical equation for this dissociation. The water above the arrow means that the NaOH is added or combined with water and dissociates into sodium, a positive cation, and one or more negative hydroxide anions. How do we know if something is an Arrhenius base? We can tell based on their chemical formula.
A few Arrhenius acids are shown here. Notice their formulas start with H. This is the hydrogen atom they lose as H+ when they dissociate in water. In acetic acid, which is often written as CH3COOH, the H that the acid loses is written at the end of the formula instead of the beginning. Organic acids are often written this way. You just have to watch for the COOH at the end of the formula in order to recognize these as organic acids. A few Arrhenius bases are shown here. Notice their formulas all end in OH. This OH is lost as a hydroxide, or OH- ion, when these compounds dissociate in water.